Interesting. All right. I think at this point, hopefully you haven't seen all my module already to the very end of the slides. So without further ado, I am Olayinka, and that's me. Don't worry, hope you're not impressed by my beautiful smile. We'll go further, and that's what I expected to see. So I'll be talking about rotation-invariant graph neural networks for skeleton-based human activity recognition. Do I need the mic? Yeah, don't. So that's my boss, Phil, who I work with on this. So the talk outline is I will go through the problem motivation, the model. I'll give a breakdown of it, and we'll look at the model itself briefly. We'll look at the data sets we are working with, some of our results and limitations, and where we'll go from here. So let's motivate the problem. If you have a football match and you want to watch a football, some of you might stay along at the very top there, just in case you are losing, you can quickly run out. And some persons might be very close to the action. And some persons even are even much more closer to the action. Some guy is very unlucky, is in front of a pillar and his view is blocked. What you normally would want is, if possible, you could see the game as it happens from every angle possible in the football stadium. And this is only possible for those of us who are at home, who can watch from the comfort of our TV and get different camera views. But for those of you who are present at the stadium, you are going to be as unlucky as this guy standing in front of the pillar. Very sad. So this is a problem generally seen in all sports and other walks of life, depending on what context of surveillance you're interested in, or video surveillance, let's put it that way. So if we take, for example, this guy who is about to pitch a baseball, and we take different camera views, we would see that we get different poses, different skeleton poses for the exact same pose when we extract the skeletons from different camera views. What we want is some model that, don't worry. What we want is some model that when we train on one particular view of the skeleton, we get a particular vector embedding. And when we test on a different view, we should get the same embedding. Okay. Yeah, there it is. When we test on a different view of the same skeleton pose, we should get the same embedding. That is what we want. So we want our model to be rotationally invariant. In particular, our graph neural network to be rotationally invariant. And how do I achieve that? Normally, when it comes to deep learning models, what happens is you have this preprocessing that goes on where there is, there it was, where there is some preprocessing, which in this case will be some transformation like rotation across different angles. But trust me, you cannot rotate across, you cannot preprocess to capture all 360-degree rotations across all plane X, Y, YZ, and XZ, right? You cannot capture all of that. So what you want instead is, instead of doing the preprocessing and then applying your model to it, you want a model that is able to capture this invariance property, where, in quotes, you can compose the rotation as part of the model. Or rather, you want your model to have its ability to be invariant to whatever orientation your skeleton data is. So how do we go ahead to achieve that? So normally we have this idea of a generator from Lie algebra. This is in 2D space, where you can take the exponent of this generator and it will give you the equivalent of a 2D rotation. Of course, you can extend this to 3D rotation matrix. And what is the essence of this, you may ask? So in order not to bore you much, I'll probably give you the full gist. So we can extend the generator to this form where we can use it for 3D as well. And if it's in its explicit form, if we are to rotate across the XZ plane, XY plane, and YZ plane. And why is this important? Is that we can combine it in all sorts of ways. to get any rotation across any space we want or any plane we want. So what does this achieve? This achieve, as you can see, is just rotating the vector, in this case, a 2D plane. Nothing interesting here, but do note what action this particular transformation brings into play. So if we look at this other case here, where, of course, the familiar Euler formula used in the complex plane, right? And we know that if we just have multiplication by I is the same as doing this, which is a 90-degree rotation. So keep that in mind. And of course, this as well in the complex plane also performs the same action of rotation. So we can confidently say that these two are equivalent, right? Whether we are multiplying by I, or whether we are multiplying by I or we are multiplying by this particular generator here, they both achieve the same thing of a 90-degree rotation. So where does this lead? If you consider a Laplace transform, where this is its general form, if we're not very strict with the definition, and we take x, no, we don't have to take it. That's actually the case. And s is a complex variable. If we take the real part of s to be 0, this reduces to a Fourier transform if you take into context the proper domain and scale. So what's the essence of whether it's a Laplace transform or a Fourier transform? What's the essence of this? Is that this exponential function here, what it does is it rotates the signal. And the essence of that is that it would extract the relevant frequency, or in this case, or in our case, the relevant angle of rotation that is peculiar to that data set. So what we got from this is we designed this, we call it an equivalent discrete function of the transform, where in place of the s here, the s variable, we have this our eta variable here. And this eta is the matrix generator we spoke of earlier, where instead of s, or rather instead of I, here we have this matrix here that also achieves this matrix rotation across whatever plane we design. So in this case, ij can be the xy plane, or the yz plane, or the xz plane. And our expectation is that it would reorient whatever feature matrix that we are working with, however we want. So how do we use this in our model, right? That's the interesting question. What we do is we have this case where we impute our feature matrix, which in this case are the 3D coordinates of the skeleton, the head, the shoulder, the legs, and we perform a linear projection. And I'll explain briefly what linear projection is meant to do. If you keep in mind that the matrix we showed earlier, it's applied in 3D space, right? The XYZ. And with deep learning models, you expect, just a very quick example of the large language models. The large here is because the dimension at which these models operate are quite high, 256, for example, or 128. So the question then becomes, how do you apply this function that you have designed to fit for these higher and higher and higher dimensions, right? So what we do instead is to project from whatever dimension our feature matrix is to a 3D. So we have so many heads of 3Ds. So if you had, say, for example, a 256, we can project it to 3D vectors, 18 of them or 20 of them, however long we want. And then we can comfortably apply our transformation across all the planes. And of course, this is the spatial domain of our model, which is applied to its skeleton. You see how. And after that, we pass that to the temporal domain. This is not an original work. This is the original work here. So instead of reinventing the way, we just took a temporal module that already works in a different model. So that's what we did. And this is the data set we are working with, the NT-RGBD data set. Keep in mind, we are not working with the video, we're only working with the skeletons. The reason why this is done this way is so that you have a proper insight as to what goes on. And if, just to mention, the benefit of the skeleton in this case is we are not bothered by the background information. Whether there's a chair there or there's a TV there, it doesn't affect the model. Whether it's dark, it's light, all of those, we call them background clutter or noisy background information, are disregarded by the model because the model just takes in the 3D skeleton input, which is what we want. So there's a part of preprocessing the data. And there's a reason why I have to point this out here is that when we go into the subsequent slides, you see how the skeletons, so unlike here, where you can see the skeletons, they are properly upright based on the position of the camera. And hope you can observe that in this case, it appears the camera is just in front of the subject. And in this case, it appears the camera is just at the side of the subject. So we have different views. We have a 0-degree view here, and we have a 45-degree view here. So because of the different camera orientation, there's a different work that shows that it's important to change the projection or the axis of the camera, the axis of the skeleton here. And if you do this, it would give you, it would take away all the views, all the variation, whether it's a 0-degree view or a 45-degree view, all of those will be taken away. You just have one consistent view for whatever skeleton you look at. But that defeats the purpose of our model, because the purpose of our model is, regardless of the view, you want to be able to classify it correctly. So what did we do instead? So let's see what this does. So what this does is it takes, so if you look at the skeleton from the camera coordinates, this is exactly what you see, right? We oriented this way. And then it applies this transformation, which is just autonomal normalization of the vectors. And then you have that cross product. And so this is just a Graham-Smith algorithm. And then you get this, right? So it's properly oriented, right? So this is nice. Even without a deep learning model, I could tell whatever the guy is doing because this is how it looks like. But we'll see where the drawback of this comes in. So what our model does is it trains on this skeleton where it is the 0-degree view or a 90-degree view, and then it tests on this skeleton, a different view entirely, right? And of course, if I didn't put the label there, you probably know what the guy is doing, so, or the lady is doing. But keep in mind that this is based on the skeleton that has been aligned. So we train on an aligned skeleton, which is this, and we test on an aligned skeleton, which is also this. And this is another example here where the bloke is saluting. So how does our model perform compared to the baseline? This is still a work in progress. Hey, so this is the baseline model. By the baseline, we mean that instead of just using a very fancy rotation-infused Laplace transform-induced model, whatever you call it, you just use that vanilla GCN, graph convolution network, nothing fancy, and you get 94.0%, right? And our model here has 94.3. The SO2 GCN, another variant of our model, 91, nothing fun. You probably say, we wasted 4 months of research doing this because that guy does better. And if we check the other results where we train on the aligned skeleton, which is what you see here, and then we test on the unaligned skeleton, which is exactly what you have from whatever the camera gave you, which in this case, the guy is still jumping, but then he's probably hanging on the wall. It's probably Spider-Man at this point. And then this guy, I don't know what planet he lives in, but if you can stand seated like this, you are no better than Michael Jackson. So you have this to be the case, where you train on this view, and then you test on this view. And the question is, how well should the model perform, given that it is meant to be rotation-invariant? That is the catch here, all right? Drum roll, praise. Okay, I think they already gave my answer. So if we check what happens, we see that the baseline actually drops to 18%. And we were able to still manage a 50.6% accuracy. Right? Yeah, not bad. Probably it would be so nice if I could say, oh, we probably were 100% even after that. But that's not the case. And you might ask, okay, whoa. So what's happening here? Well, obviously the model has something that this baseline doesn't have, right? And as I said, these three are variants of the same model. We just did something differently. So rotation invariance is right around the corner for our model, as we can rightly see. Notice that here we have this rest connect, which is like a residual connection, a slip connection. You see it in some earlier slides in the model. So in this model here, we have a residual connection attached. Here we have no residual connection. So both models are the same. They have 6 partitions of angles. And when we had a residual connection, we have a very high accuracy, but of course, the invariance property was diminished. When we have no residual connection, the general accuracy is lower, but the invariance ability is still maintained. And when we increase the partitions to 20 partitions of our angles, of course, the accuracy is still low. Take note, there's still a residual connection here, but then we have a higher accuracy. And then you ask, okay, why not just go a step further and do 20 partitions still, and then remove the residual connection? Maybe you probably have 70 at this point, right? That'll be the next stop. But of course, the experiment is failing for whatever reason at the moment. So we'll probably explain that in details later on. So just to point out that the skip connection is good for training, but corrupts the invariance property, as I highlighted here. Okay, and then a larger partitions improves rotational invariance for our model. But just to point out about the skip connection. So here is a paper. All right, yeah, this paper here talks about what happens to the loss landscape of your model when you include a skip connection. So what it does is it just smoothens the loss landscape, and you can get to your minima as quickly as possible. But of course, you can see that the loss landscape is greatly changed. This is different from, it's like day and night, right? So what we believe is by including the skip connection, yes, we're able to achieve the minimum, but whatever the model would have learned by changing its weights to be able to climb over these valleys and these hills and all the like before getting to the optimum, whatever it would have learned to achieve that is lost completely by including a skip connection. So the current challenge we're currently facing with the model is how can we increase the partition as high as we need to without including the skip connection? So that is the difficulty we face, and the model is misbehaving for some other reason. So yeah, future work would be to adopt other form of transformation. In this case, we only use rotation. We can also include shearing, which is seen as in some of the skeletons when you look at in the wild data set. Data sets you just gather from YouTube and just extract the skeletons. The camera can be this way, the skeletons can be this way. And you want a situation where, regardless of how deformed your data set is or your skeleton is, the model can still correctly classify it. So aside the rotation invariance part, can we also put other form of invariances based on any other transformation? And yeah, we can. So in the other case where we learned the generator, we use a generator that would induce a rotation matrix. We can also learn a generator that is relevant to the data set. And for now, we are only doing geometric learning, trying to transform the skeleton itself. But instead, why can't we just leave the skeleton and just go to the embedding entirely? Which in this case, we just focus on the manifold and see what turns out when we do that. Okay. Thank you very much. This is me and my boss, and this is funded by the Intense Maps project. Any questions?
Thank you very much, Olayinka. Any questions?
Is this just for is there like a specific application in mind? Obviously, you've got these things which are more video based, but I'm wondering if you have a specific, maybe like a medical kind of application or something like that. Is there someone specifically said, listen, we have this problem and we'd like you to solve it? Or is it more of like a general sort of kind of thing that you've come up with?
All right, that's a very brilliant question. So a quick disclaimer here is that rotation invariance models they are not new, right? And there are different applications where we want the model to be rotationally invariant. So how do we induce that property? right? There are those who do, maybe they do some stuff in atomic physics where they try to obtain the properties of an atom, and assuming that those properties remain the same regardless of how oriented the atom is in space, right? So they find a way to induce rotational invariance. And if you keep in mind, when I said atom, you could assume that they could also be designed as modeled as a graph, right? You have nodes and the edges, or in this case, the bonds and the atoms, wherever they are. So in that application there, it is useful, right? Now, I'm working with skeletons here because in this domain, it hasn't been considered or considered more broad, or it is assumed that, oh, if you just train on this data set has different camera views, your model should be able to learn this rotational invariance implicitly. And we've shown that that's not the case, right? Because if you consider the unaligned skeleton, as we showed earlier, it fails entirely. Now, finally, to address your question, medical use case, I would assume yes, that is possible, provided you can get the data to be points data. If you observe, the skeletons are coordinates of the joints, right? So other use cases, for example, could be in self-driving cars that use LiDAR to obtain point clouds data. Because they are points, they can easily be oriented. But when you have images, like for example, a CT scan or any images that is just your regular 2D, the best you can get is this rotation. You cannot get any additional dimension to the rotation. So in that context, I don't know how well it will work, but provided the data is point cloud, so it's a points data, we assume that this method should be transferable to those other problems as well.
Cool.
Yeah.
Thank you.
Another question? Let's thank Olayinka again.